irrigation engineer. Every year on his birthday, the Telangana State Centre Committee at its meeting held on 24th August 2019 has unanimously resolved to organize an endowment lecture annually at our center in honor and the memory of an eminent engineer, Gurram Koti Reddy garu. He is superintendent engineer retired, irrigation department. Accordingly, the Telangana State Centre is organized already first endowment lecture was delivered in memory of Gurram Koti Reddy garu on 23rd 9th 2019. Now we are celebrating second endowment lecture. I am very glad to brief about the Gurram Koti Reddy garu to all the participants. Engineer Gurram Koti Reddy was born on 23rd September 1925 in Tipparthi village of Nalgonda district to Papa Reddy and Seethamma. After matriculation at Nalgonda, he completed BA and BE Civil Engineering from Usman University. After completion of graduation Civil Engineering, I joined in the Tungabhadra project. After bifurcation of Hyderabad State in 1956, he got transferred to the NSP and he was in charge in Chilkarurti Tunnel. He was transferred to Amshadaya Project Investigation Division 1970 as a punishment for his support to the Telangana agitation in 1969. He worked in SRSP as a EE. After promotion as SC in 1975, he is posted as a project administrator of NS Left Canal. In 1979, he is posted to CCH and retired in 1983 after completing Kakatiya Canal from land came 234. And already explained, he is married to Susila and in 1944 and having 3 sons and 2 daughters. Eldest son Satyanarayana Reddy is civil engineer and second son Dr. Ramesh Reddy in USA. Third son is Pratap Reddy, is computer engineer in USA, and the eldest daughter Aruna and youngest daughter is Geeta. And Gurram Reddy garu, that Koti Reddy expired on 26th 6 2003 at the age of 78 years. He will be remembered as a dynamic taskmaster and able administrator. And we are every year we are conducting this endowment lecture on his birthday at our center. I am very glad to inform that Telangana State Centre, the Institution of Engineers, has regularly organizing the almost 17th endowment lecture every year on the birthdays in honor of the eminent engineers. And accordingly, these endowment lectures are being delivered by the people of high eminency with considerable professional experience to throw lights on important emerging topics of today's relevance. Then with these few words, once again, and extend hearty welcome to our chief guest and also speaker, Professor V L SUBRAMANIAM, Professor, Department of Civil Engineering, IIT, and to all of you for this endowment lecture. Now, I am requesting Sri V Jambul Reddy FI, a member IEA Telangana State Centre, introduce our chief guest and speaker of today's endowment lecture to all the participants. Over to Jambul Reddy garu.
Good evening, everyone, all engineers. So, I am very happy to introduce myself. I am V Jambul Reddy, a committee member and former engineering chief of Agriculture Department, Hyderabad Metro Water Supply Sewerage Board. I am very thankful to the Institute of Engineers for giving opportunity to introduce today's speaker, today's chief guest, Dr. V L SUBRAMANIAM garu, on the occasion of Gurram Koti Reddy second endowment lecture. Sri Professor V L Subramaniam Garu is currently a professor in the Department of Civil Engineering at Indian Institute of Technology, Hyderabad. He was the Dean, Planning and Development at IIT Hyderabad and oversaw the construction of the new campus. Prior to joining IIT Hyderabad, he was a professor and cattle research fellow in Department of Civil Engineering at the Grove School of Engineering, the City College of New York. Dr. Subramaniam obtained BTech in the year 1993 in Civil Engineering from IIT Delhi and PhD in Structural Engineering and Materials from Newarton Western University, Evanston, USA in the year 1999. After graduation, Dr. Subramaniam worked as a research associate at the NSF Center for Advanced Cement-Based Materials. Dr. Subramaniam was awarded the Early Career Award from the National Science Foundation of USA for investigating the early age changes in cement materials. He received the James Instrument Award from the American Concrete Institute in the year 1997 for his research on non-destructive evolution of concrete. He is the recipient of the Outstanding Young Researcher Award at the Grove School of Engineering in the year 2006. He was the chairman committee 215 in the fatigue of concrete of the ACI in 2009. He was elected a fellow of the American Concrete Institute for notable contribution of the area of fracture and fatigue of concrete. He is an associate editor of the Journal of Materials in Civil Engineering and has served as an associate editor of the Journal of Bridge Engineering of the American Society of Civil Engineers. He is on the editorial board of the Journal of Cement and Concrete Composites. He is a life member of the Indian Concrete Institute. Professor Subramaniam is currently the director of the Center of Excellence in Sustainable Urban Development of Ministry of Human Resource Development at IIT Hyderabad. He is the program leader for the Sustainable Development Trust in the Friendship Program of the Japan International Cooperation Agency. He is the recipient of Excellence in Teaching Award at IIT Hyderabad in 2011 and 2015. He has served as an advisor to several agencies, including RIDES, RVNI, Hyderabad Metropolitan Development Authority, AP Capital Region Development Authority, IEITSC, US Consulate in Hyderabad, and CPWD, Campus Development of the Kanpur Development Authority. Under Subramaniam Garu, under him, 9 persons awarded PhDs under him, and he has published about 100 papers. Thank you very much for giving this opportunity. I am handing over to the chairman. Thank you for further action.
Thank you very much, sir. Thank you, sir. With the permission of our chief guest, just I want to tell that Venkatramaya SC Irrigation want to say about few words about Koti Reddy, sir. Over to Venkatramaya. Sir, మీరు అన్మ్యూట్ చేసుకోండి సార్. మీరు అన్మ్యూట్ చేసుకోండి సార్ మీరు. ఓకే, నౌ యూ కెన్ టాక్.
సభకు నమస్కారం అయ్యా, సభకు నమస్కారం.
వినిపిస్తుంది సార్, వినిపిస్తుంది
సార్. సభకు నమస్కారం. నేను కోటిరెడ్డి గారి దగ్గర 1967లో ఒక 1 year పనిచేశానండి జేఈగా. ఆయన లీడర్షిప్ క్వాలిటీస్ అవి మమ్మల్ని బ్రహ్మాండంగా ఇంప్రెస్ చేశాయి. మేము ఆయన అడుగుదాడు నడిచే ప్రయత్నం చేశాము. ఒక చిన్న ప్రాక్టికల్ ఎక్స్పీరియన్స్ ఏంటంటే, ఒకసారి చిన్న ట్యాంక్ బండ్ డిజైన్ చేసి తీసుకొచ్చారు నా దగ్గరికి. నేను దాన్ని అగ్రి కాల, అయ్యా ఇది ఎవాపరేషన్ లాస్ ఎక్కువ పనికిరాదని చెప్పా. కోటిరెడ్డి గారు దాన్ని శాంక్షన్ చేసి కన్స్ట్రక్ట్ చేసి ఒక 8 నెలల తర్వాత ఎండాకాలాన్ని తీసుకెళ్ళి చూపించాడు. ఆ ట్యాంక్ చుట్టూ సీపేజ్ వాటర్ వచ్చి ట్యాంక్ నిండుగా ఉంది. అందువల్ల అన్నాడు, పుస్తకాలే సరిపోదు నాయన, కాస్త ప్రాక్టికల్ అవుట్లుక్ కూడా ఉండాలని చెప్పాడు. అలాంటి మహానుభావుడికి నమస్కారం. చాలు. థ్యాంక్ యూ సార్.
థ్యాంక్ యూ సార్. థ్యాంక్ యూ వెరీ మచ్ సార్. నౌ క్యాప్టెన్ జనార్దన్ రావు సార్ కూడా మాట్లాడతారు. జస్ట్ 2 minutes సార్.
సార్ వచ్చిందా రాలేదో ఇంకా అది నేను అనేది
వచ్చినట్లున్నాడు. ఓకే సార్. సార్ లేనట్టు విల్ స్టార్ట్ ద
ఓకే ఓకే తర్వాత మాట్లాడేది.
Yes sir. Now I am requesting Professor V L SUBRAMANIAM FIA, Department of Civil Engineering. Please start your talk.
Thank you, IEI, Telangana Center, for giving me an opportunity to present.
అందరికి అన్మ్యూట్ చేయ బాబు. మ్యూట్ చేసే.
Okay. Thank you, IEI Telangana Chapter, for giving me an opportunity to present. I
am requesting please mute yourself. Yes sir.
Okay, thank you, IEI Telangana Chapter, for giving me an opportunity to present, and thank you, Rameswara Garu, for considering my for me for this endowment lecture. And let me start by sharing my screen. Right. So let's see.
Full screen better, sir.
Okay, so now I'm in the presentation mode, and again, thanks once again for giving me a chance to present. It's a topic that I'm very passionate about, and that is concrete structures and innovations that are taking place in concrete materials and concrete technology. And because sustainability has become a buzzword, where we are all talking about sustainability, sustainable construction, I think it's important that we have to put things in a perspective, look for sustainable construction. So with this brief, this thing, let me get started with where we are, where we were, where we are going. So if you look at construction, and I'm focusing at this moment on the super tall buildings, starting from 1930s, which is on the extreme right, to the extreme left, if you go, this is the tallest building on the planet today, which is Burj Khalifa. Now, one thing you see, of course, is that the skyline has steadily been increasing in height. And Burj Khalifa, to give you a point of reference, is about 850 meters tall. So it's almost a kilometer in height. Now, we are literally pushing the envelope here. So in terms of what we are able to achieve in construction, it is not just merely that we're going high, but we are actually pushing the envelope in terms of several technologies which need to concurrently be possible for us to put a man basically living happily at 850 meters, which includes, of course, the construction technology. Now, if you go to construction technology, starting in 1930s, most of the high rises or super talls are built with steel. The structural system was steel. As we start coming to the left, we start seeing, we start walking across in decades. So starting from 1930s, then we come to 1970s, 80s. So even up to 1990s, the material of choice for super tall buildings was steel. But something happened, and there was a major revolution in concrete. There was a major revolution in the way we were producing concrete, the way we were using concrete, the way we were actually able to place concrete, that if you start looking at 2004 Type A 101, which is this building, the green building that you see here, to the left of that, practically all the buildings have major structural system, or the structural system of those buildings is concrete. So concrete has now become the material of choice in these super tall buildings. And that has happened because we are able to develop technology to make concrete stronger. We're talking about concretes which are very, very strong today, concretes which are very ductile, because if you look at a super tall building, like what you have here in Burj Khalifa, the wind pressures are so enormous at that height that just under the design conditions, Burj Khalifa, the top would sway almost 2 meters relative to the base. So now the materials have to be able to withstand that kind of lateral movement. So we are talking about concretes which are basically able to handle that kind of requirement for flexibility. And finally, of course, we are able to place the material so high. So now I have technology where I could be sitting on the ground floor and I'm able to pump concrete to a height of 800, 850 meters, even 1 kilometer. So that technology is also available now. And that is what has made concrete the material of choice going forward. Of course, concrete has inherent advantages over other construction materials. It is its cost. It is the cheapest construction material that you can possibly think of. Fire resistance, it is one of the best known materials when it comes to fire performance and fire endurance. So coupled with all of these things, now when technology is enabled, that gives us the performance and the ability to deliver the material at whatever height we are talking we want, we are now thinking of concrete as the material of choice for high-rise and super high-rise construction. So now if you look at some statistics and use of concrete, and if you look at the super tall structures, if you look at the 100 tallest buildings in the world today, 59 of them are in Asia and 23 are in Middle East, which leaves only 18 of them in the rest of the world. So which basically tells us that the major action when it comes to super tall buildings is in Asia. That's where all the action is. So for once now, the technology advancement, technology development, implementation is all taking place in Asia, whether it is Southeast Asia, South Asia, South Central Asia, or Middle East Asia. So that's where all the action is. If you look at numbers coming out of Dubai, which has perhaps the largest concentration of super talls, 93% of super talls in Dubai have essentially concrete building systems. Now, two of the tallest buildings in the world, Burj Khalifa, which is 850 meters tall, and the Jeddah Towers, which is under construction. And when it is complete, it will be 1 kilometer in height. Both of them, both of these buildings, both of these super tall structures use concrete structural systems. So just to show you a distribution of how concrete has emerged as the material of choice for construction. So in this bar graph, if you look at the extreme left, 1930s was when the super tall construction started. Empire State Building was built in the 1930s. In that decade, if you look at the color is light blue, which basically means that steel was the material of choice when it came to super tall constructions or tall buildings. As we walk across the decades, going from 1930s to 1940s and so on, by the time we come to our current age, 2010, 2018, now concrete is starting to replace steel as the material of choice, and steel only has basically shrunk in proportion of usage in the super tall buildings. Concrete is basically now 63% of the super tall buildings or buildings which are taller than 200 meters are basically built with concrete structural systems and are made of or built with concrete. And then there are other alternate forms of construction like composite construction, where we use steel and concrete together for a very efficient structural form and structural systems. Those are between composite and pure concrete systems. They're basically the bulk of the constructed super tall buildings are made up of these two forms of construction. Now, the reason this has become possible is because of the advancements we've been able to manage to achieve. Advancements in concrete strength. We are now able to produce concretes which are very strong. We have made tremendous advancements in pumpability of concrete. Now we are able to pump concrete to great heights. We can pump concrete to a height of 800, 850 meters. Of course, and affordability in terms of cost and overall economy, concrete is the cheapest construction material. And several construction techniques, and I'll lay some emphasis on this later in my talk, as to there are construction techniques that are now available, which are not only speeding up construction, but actually are giving way to what we call form-free construction, where one can literally go from the drawing board having a constructed structure. So we are bringing in digital technology, we're bringing in 3D printing, we're bringing in digital manufacturing technology to basically construct concrete structures the way one would actually assemble or print a mechanical part. So all of that is now becoming possible because of advances that we are able to do with material processing. And that's where the whole story starts. So going forward now, just to give you a brief overview of what is concrete and where it is used. Today, concrete is the most extensively used construction material in the world. It is the second most large or widely used material on this planet. Basically, it is second only to water in terms of its consumption. And if you look at the total material usage, we consume about 2 tons of concrete for every human being on this planet per year. That is the amount of concrete that we produce. And its usage on this planet is second only to water. Now, if you look at India in particular, we're talking about a $5 trillion economy. That is our dream. Now, this is an old report that came from McKinsey, which was basically an older report, which came out in, I think, 2007, 2008. And around that time, they basically had projected that if India is an aspiring financial superpower, then they have to invest in their infrastructure. And their projection at that point of time was that India would have to invest close to $2 trillion in their infrastructure. Without infrastructure, there is no economic growth. We cannot dream of 7 to 8% sustained economic growth without providing the infrastructure that is needed to sustain the growth. And recently, of course, Niti Aayog has looked at this problem more seriously, where infrastructure is getting a big push, because it has come to realization that we cannot have a growth in our economy, the projected growth, and become a $5 trillion economy unless we are willing to invest money in our infrastructure. And when it comes to infrastructure, concrete is the material of choice, which means we have to look at concrete very closely. We have to be able to look at producing this concrete in the volume that we want to be able to put all that infrastructure in place so that we can sustain the economic growth that we're talking about, so that we can catapult ourselves from a $1 or $2 trillion economy to a $5 trillion economy. So that's the backdrop of the material concrete and the role it is going to play in our economy. Now, one of the issues with that, with the requirement of concrete for infrastructure is that concrete is made with cement. And this graph here shows the cement production. Now, if you look at the red here, red is China. And if you look at China today, 2020, China is the largest producer of cement in the world, followed by India. The blue is India. So we are basically the second largest producer of cement in the world. In fact, India produces more cement than US and Europe combined. So we are even today one of the largest consumers of cement. And of course, we are second only to China. Now, where did all this cement in China go in from? So starting from 1990 up to 2020, for almost 3 decades, China was the leading producer of cement. And none of this cement was being exported. It was being consumed internally, domestically. All of this cement was going into making concrete, which went into making their infrastructure. Today, if China is a $12 trillion economy, it is because of the infrastructure they have put in place over the last 3 decades. And now, if you look at this graph here, India's projected demand up to 2050 is basically going to take us into a territory where by 2050, we will be the largest producer of cement. And we need this kind of cement production to produce the infrastructure that we're talking about. For all the infrastructure facilities that we're talking about, whether it is the high-speed train project, whether it is the port facilities that are being talked about, whether it is the dams, the road network, all of these, the transportation network, and even housing. So the housing solution that is needed for housing the large population that is migrating into urban centers. So we need a lot of concrete. And for that, we need a lot of cement. One of the biggest problems with this requirement of cement is actually threefold. It's not just one problem. And we need to overcome these problems in order to sustain the production of cement so that we can hit our economic, the target of tripling our economy in the next 20 years. Now, what are the challenges with cement production? One of the biggest challenges with cement production, and of course, our projected need of cement in 2050 is going to be 750 million tons per annum. That is the volume of cement or the amount of cement that we'll have to produce. Of course, it's a projected number, but the projected number is based on a realistic estimate of what we need to put in place in the form of infrastructure. So now to meet the 750 million tons per annum demand, we need to be able to produce the raw materials which are needed. And one of the primary ingredients, raw materials for cement production is limestone. Now, our current available estimates of limestone are only going to last us 35 to 40 years. It's very well known, which means that we may run out of limestone before we ever are able to produce all the cement that we need for putting our infrastructure in place. The second problem is the energy requirement. Cement is an energy intensive material. We need a lot of energy to produce cement. So we need to then constantly look for sources of energy to be able to sustain the production of cement. And the final thing is the carbon footprint that goes with cement production. And cement has a very large carbon footprint. And the number is that 1 ton of cement produces almost 850 kilograms of carbon dioxide. So it has a very large carbon footprint. And depending on the source, cement production is the second or the third largest anthropogenic source of carbon dioxide in the atmosphere. It is the second or the third largest man-made source of carbon dioxide in the atmosphere. So now, with all the environmental constraints, then cement production does become a challenge in the future. How do we keep producing cement while we are producing so much carbon dioxide and while we are pumping out so much carbon dioxide into the atmosphere? And how do we then also produce cement with these limitations of limited resources of limestone and also having the energy demand? So this is a problem that we as people or as people researching in concrete are very well aware of, and we've started working on this, and this has taken several forms. So just to show you, normal cement is made with clinker and it is ground with gypsum. That is typically what cement is made up of. It's 95% clinker and 5% gypsum. Now we are already starting to look at replacement strategies for cement. So the idea is to produce cement which uses less clinker. It is the production of clinker that uses limestone. It is the production of clinker that is associated with the carbon footprint. It is the production of clinker that is associated with the energy requirement. So one of the things to do would be to look at replacement of clinker in the cement. And that is being now we are looking at the replacement of clinker with waste materials like fly ash and slag, both of which are basically post-industrial waste materials. And we are able to produce cement such that we are reducing the clinker factor in cement. We have now, through research, managed to reduce clinker factors in cement, sometimes down to almost 30% to 40% of the original clinker requirement of normal, ordinary Portland cement. So that is already happening. Now, what that allows us to do is to stretch our resources significantly, where basically we're able to stretch what is available, reduce the environmental impact, and reduce the energy requirement in cement. So that is one way that we are looking at trying to become more sustainable, where we basically are able to stretch the material to give us the required performance. Now, So now there are other cements that are being looked at. So we are looking at alternate cements. The alternate cements that are coming in the market, basically, one of the cements that is already being produced commercially goes by the name LC3. And this has a lower clinker factor. We are reducing the clinker factor quite a bit, down to 50%. And we basically use calcined clay. And the clay that goes in here is basically poor grade clay. This is not clay that is used in agriculture for agricultural purposes, but it's clay that is typically found as mine overburden. So using these materials, then we are able to produce these cements which have much lower environmental impact. Then we are also looking at alternate cements, where we are looking at producing cements using only waste materials. So, and now these cements have become reality, where we can use fly ash or slag, which are primarily waste materials or post-industrial waste materials. These are materials that are produced as a byproduct of some other process. We are able to use those materials and we are able to start producing cements. And these cements rely on a process called geopolymerization, hence the term geopolymers. And these cements are also coming online. Now, the biggest advantage of using these cements is that we utilize waste produced by another industry. So basically, there is no carbon footprint associated with this material, and we are producing material that is required. So basically, it kills two birds in one shot. So that work is also going on in parallel, where these alternate cements are being explored and are being developed for commercial use. Now, that is as far as the material challenges go. Now, what about concrete? The concrete, one of the biggest challenges that we have in concrete is when we place concrete, we need to put it into formwork. So we have to basically arrange shuttering and we pour concrete into the shuttering. And then concrete takes shuttering that we place. So if I want a beam, I basically put the shuttering in the form of a beam and I pour concrete in there. And then eventually when concrete hardens, it takes the shape of the beam. Now, one of the biggest disadvantages with this is that I'm limited to rectilinear shapes. I'm basically limited to shapes which are rectangular in cross section, because on site, it's very difficult for me to form complicated shapes. So that is one of the biggest disadvantages of concrete. The disadvantage lies in the fact that rectangular shapes are not most efficient. They basically have a high material usage. If I want an efficient structural shape, I'm better off using an I or a T shape. Now, but forming I or T shapes in the field is very difficult, and that's why we end up using these rectilinear shapes, and that basically is leading to inefficient use of material, resulting in heavier structures and basically overall inefficiency in terms of material usage. So that is one of the biggest challenges in construction, is how do we make this process of construction more efficient, whereby coming down to using the material more efficiently. And the question is, what if the most efficient shape is what is shown here on the left hand side? What if the most efficient shape of the column happens to look like a twisted shape as I've shown here? Now, doing this on site is practically impossible with our current construction technology, which means that we actually have to develop construction technology, construction methodologies, which will allow us to produce these shapes on site, which basically which takes us into a completely new domain. And that is these are the new developments that we are working on in terms of concrete construction technology. So some of the other challenges with concrete is that we basically use formwork for construction. And what that does is we basically have to assemble the formwork. We have to put our steel and tie the steel work. And that is a very time consuming process. So, and it also requires a lot of labor. So one of the other challenges that we are facing in concrete construction is, can we speed up this process? Do we really need formwork? Do we really need shuttering? Do I need this reinforcement in the form of mesh, which has to be brought in place, tied in place? Can I speed up this whole process? And so that is where we are looking now at form-free construction, where I don't need formwork. I can simply come and I can take an AutoCAD drawing and I can print a structure that I want to use. So that is the ultimate form of technology that we are all pursuing. So now concrete, if I look at concrete construction of the future, what we are looking at is make concrete responsive to the requirement. So previously, when I was a student, we were taught concrete as a 1-2-4 or 1-3-6 mixture. That is it. We would mix concrete by in certain proportion of the ingredients, which was cement, water, and aggregate, and we would hope that we got the strength. That is it. And it was just some material that gave strength. But now we are revising our outlook on concrete, where we're saying it is no longer enough for concrete just to mix and deliver strength. We want concrete to be responsive to the requirement, where we want to be able to tailor the delivery and placement of this material. That is, I want to be able to engineer the material so that I can deliver it in the way, shape, form that I want. And once it is in use, it should ensure the performance. It should basically give me a long-lasting structure up to infinity. Essentially, that is what we are looking at in terms of our concrete construction of future. So with that, now we have now moved into what is known as performance-based design. So in concrete now, we are moving into performance-based design. Conventionally, we used to use prescriptive requirement of strength. We would say, well, I need M35 grade of concrete, or M40 grade of concrete, or M60 grade of concrete. These are all grades of concrete. They're all prescriptive measures of strength. And basically, that's how we designed our structural members. Members would be designed using concrete of a certain grade. And we were designing our structural members for strength. But that is now shifting. Now, strength is only one of the performance criteria. What we are saying is, design criteria are expressed in terms of achieving performance objectives. So it's not just enough for the concrete to meet strength requirement. Of course, the structure has to be strong. Of course, the structure has to be able to withstand the effect of whatever extreme event that is being applied to the structure. But it should deliver on performance objectives. Now we're talking about performance objectives, not just in the hardened concrete or when the concrete is used in a structure, but we're talking about performance during formation and placement. This has also become very, very important. I want concrete to behave in a certain way while I am making the structure, while I'm building the structure. And it should basically give me a long service life. So performance during service life, both of these have now become important. So we're talking about performance measures of concrete. And when we talk about performance measures of concrete, we talk about performance measures of fresh concrete. So we're talking about flow, pumpability, filling ability, these have become very, very important now. We want concrete to be pumpable, and I'll give you some examples of where this has been implemented. I want concrete to flow. I don't want to go around vibrate concrete, and I want concrete to fill the entire formwork very quickly. Then in hardened concrete, once concrete has become hardened, it should deliver on strength, which is of course something we are doing even today, but it should ensure long-term durability, that it should be very durable. It should give me long-term performance. And if I am able to hit all these performance measures, then I get assured performance, not just in the short term, but also in the long term. So performance specification now is also shifting to the considering the material perspective. Performance specifications were already in use in structural performance, where we were designing structures for specific performance in seismic, wind, and other extreme events. But now we are bringing that even into the materials perspective, where we're talking about formability of the material. How formable is the material? Can I form it and give it any shape I want? Placement and speed. How fast can I place the structure, place the concrete, and how fast can I deliver the structure? And of course, the long-term durability. Once the structure is in use, how durable is it in the long term? So just to show you some of the performance requirements that are put in place in some of the marquee or the noted buildings. Now, Burj Khalifa, the pumping of concrete was achieved for a height of about 601 meters. So basically, concrete was pumped for a height of almost half a kilometer. Now that is an achievement in terms of materials, because if you take concrete, it is made up of cement, water, and aggregate. And if I try to pressurize the material to create a head of 601 meters, basically it will start, the material will start to segregate. Water will go separate, aggregate will go separate, and cement will go separate, because under that high pressure, these three materials have three different specific gravities, and then it tend to segregate. Now, how do I keep this mixture homogeneous so that it flows as a homogeneous mixture? There is no segregation happening over when I'm trying to raise the head to about 600 meters. That is the challenge, and it requires material design. How do I design the material so that I'm able to achieve this? Now, in the superstructure, One World Trade Center, this is in New York. This is a structure that replaced the World Trade Center. Basically, concrete was pumped for 103 stories in a single pump. It was lifted about a height of 103 stories in one single pump. So that requires performance requirements from fresh concrete. Now, just to show you what are the specifications that were put out for the One World Trade Center. Specifications put in place were that concrete had to be made with less than 236 kgs of cement per cubic meter of concrete. Now, this is a very low number. Now, most of us who do use concrete and who have done concrete mix designs know that at the very least we use 300 kgs of cement per cubic meter. Otherwise, we use 350. 236 kgs of cement per cubic meter is a very low number, but this was specified. It was specified to the contractor that he or she could not use more than 236 kgs of cement per cubic meter. Not just that, concrete up to 40 floors had to achieve a compressive strength of 80 to 95 megapascal, and the upper floors had to achieve a compressive strength of 60 to 70 megapascal. So the contractor had to deliver a concrete mix design which achieved a really high strength of 80 to 95 megapascal using a low amount of cement, or a very low weight of cement per cubic meter of concrete. Now, that of course requires very careful thought of mix design, where supplementary cementitious materials have to be used, slag and fly ash. Optimization has to be done. Careful mix design has to be done in terms of packing of aggregate and cement in order to achieve these specifications. In addition, there were performance requirements that were put in place. The performance requirement was that, of course, there was some slump flow requirement, but the ability to pump. It was required that concrete should be concrete in the first 15 floors. Concrete should be pumpable for 15 floors for the 95 megapascal mix. And the 80 megapascal mix should be pumpable for 40 floors. This was put in as a performance requirement for fresh concrete. So whatever concrete came on site, it should be pumpable. That is, I should be able to lift it. If it is an 80 megapascal concrete mix, I should be able to lift it 40 floors in a single pump. So that is a performance requirement of this concrete. The other performance requirement that is put in place was to minimize the heat of hydration. The maximum heat that the concrete could produce is only about 70 degrees Celsius. This becomes very important because the podium, the basement raft of this structure was almost 3 meters deep, and this very stringent requirement of very low heat produced in the tower was put in place for the concrete mix that was developed. So now that means that the contractor basically had to hire a specialist concrete mix designer who could now deliver concrete that met these performance requirements going forward. So now, how does one go around now meeting these performance requirements? So the only way that one can meet these performance requirements is basically by bringing in additional materials. So if you look at concrete, it is the basic combinatrix of cement, water, and aggregate cannot achieve what I just talked about. So I cannot deliver on the performance just by thinking of concrete as cement, water, and aggregate. The age-old philosophy of 136 or 124 concrete will not deliver what I talked about. What we need is basically, this is what is now expected from concrete. I want concrete to flow like water. I want it to set on demand. I want it to gain strength rapidly. That is, I want it to basically be rapid strength gaining so that I can turn around structures much faster. I can have 3-day slab cycles instead of 7 or 14-day slab cycles. The concrete should be durable to infinity. That is, once I cast the structure, once a structure is put to use, I forget about it. It basically retains its original level of performance over the long term. It looks like new without maintenance. That means the material should have some kind of self-cleaning, self-cleansing ability. It should not attract fungus. It should not attract dust. It should have some of these abilities to clean and basically rejuvenate itself. And of course, all of this has to be achieved at a low cost. So I cannot now start driving up the cost because then nobody is interested in the material. So these are what is now, or these are the requirements that are now becoming quite common and most common expectations from concrete in terms of its usage in structural applications. How do we do this now? So since the basic combinatrix does not work, we have to start using admixtures. And these admixtures have started coming up into the market now. These are chemicals which are highly specialized chemicals. They are engineered chemicals which are engineered to improve specific properties of concrete. And small quantities of these admixtures can produce significant improvement in performance of concrete. So what is this admixture? Basically, admixture can be either a chemical or it's also a mineral admixture, depending on the origin. It is added to to concrete, and basically it modifies the fresh mixed property, setting behavior, or the hardened properties of concrete. And practically all concrete that is made today contains admixtures. So now when it comes to requirement of admixtures, because I'm targeting specific performances, so we look at admixtures as enablers of performance. So they are basically performance enablers. I'm trying to target specific improvements in performance with the use of these admixtures. So when it comes to performance, I'm talking about performance in the fresh. So I'm talking about rheology control. So I'm talking about the flow behavior of concrete. Can I engineer that to achieve what I want in terms of buildability, in terms of placement, in terms of pumpability? Then, of course, I want to also enhance the performance of mature concrete or hardened concrete in terms of strength and durability. So in the first part, I want to look at this performance modification in terms of fresh concrete. And of course, there's a whole list of admixtures that are available. And the list is basically ever growing. Every other day, we see a new admixture that has come into the market. And basically, these are enhancers of fresh concrete performance. The concrete performance, when concrete is still fluid, it's when we are placing the concrete. And that's what we are trying to enhance. So we are basically looking at placement and production control. How do I gain control over the placement and production of concrete? So gone are the days when we are looking at concrete at simply mixing and dumping it into the formwork. Now we are using words like placement and production. That's what has come into the jargon now. So when it comes to transportation and placing of concrete, we're looking at construction performance during placement itself. And now we are expecting, like I had shown before, performance in pumping. I want concrete to be pumpable, and I can specify the height, but the material should give me a homogeneous mixture that can basically withstand that pressure without segregating. I'm talking about concrete that can self-level itself. That is, it flows like water. It fills the form. I don't need to vibrate it. And then the final goal for all of us working in this area is formless placement. Can I actually do concrete where I simply mix it, I print it into whatever shape I want without having to use a form or formwork or shuttering? So let me just quickly take a look at what are some of the admixtures that are used. The most common admixture that has now become quite common in usage is the water reducer. It basically reduces the demand for water. And what that does is by adding a little bit of this water reducer, I'm able to increase the flow of concrete. And basically get concrete to flow instead of slump. So this is how concrete looks like when it slumps. It basically still retains the shape of the cone, but when it flows, it basically spreads. And that's what I'm trying to achieve. And basically, if I look at cement paste without that mixture, it is a paste, but it's a very viscous paste. And I'll have difficulty trying to empty it out of this beaker here. But the minute I add a few drops of this water reducing admixture, I'm able to get it flow like a very thinly viscous liquid. It starts emptying the container very easily. So this is rheology control or the flow control that I'm achieving by adding just a few drops of this water reducer. It's a chemical, and this is basically the role of the water reducer that is shown here. So the water content is shown on the x-axis, and the flow is shown on the y-axis. So if I make concrete, and if I increase the water content, I achieve a certain flow that is shown by the red line. But I can reduce the water demand. That is, I can achieve the same flow with a lot lesser amount of water in the concrete, as shown in this blue line here. So my concrete with the high range water reducer, HRWR stands for high range water reducer, basically gives me the same flow with a lesser amount of water, hence the term water reducer. Now, these polymers and these water reducers, these are chemical admixtures, and these are very highly engineered chemicals. In fact, they're very, very complex chemistry of these molecules. We have, these are engineered. So they're basically made up of these comb polymers with these teeth, and the specific composition of the teeth and the comb, the spine, these are all engineered so that I can achieve dispersion of cement paste very easily by steric hindrances that are created by these molecules. And these are very, very complex molecules that are specifically engineered. And a lot of work is now going on these engineered chemicals to achieve the performance enhancement that we're looking at. So how does that beneficiate concrete? Well, this is concrete, and this is very typical of what happens in concrete. When I have very heavy congestion of steel, placing concrete through the congestion of steel becomes very difficult, and I end up with these large holes, bugged holes, gaps, voids, etc. Now, of course, if you're a good contractor, you do what a good contractor does, and that is you simply plaster it and make everybody believe nothing happened. But plastering simply does not take care of the filling that is required inside the structure. So how can we overcome this problem? And high slump will not help, because simply increasing the slump does not address the problem of flow. We need concrete that can flow very easily. And here is another problem where concrete just did not flow. It was high slump concrete. This is a pile, a board cast in situ pile. The steel reinforcement was lowered into the pile and concrete was placed from the top. But as you can see here, when the pile was exhumed, when it is pulled out of the ground, concrete had not penetrated through the reinforcement. And now the entire structure is standing on this pile. So, well, I mean, that's one of those things for everybody to think about. How safe is that structure? So what do we need then? We need concrete that can perform. We need concrete that can flow through these small gaps between the reinforcement and fill the entire space that's available to it. So that basically is a performance requirement from concrete now, that I need self-filling, self-flowing, self-leveling performance attribute of concrete. But how do I get that? If I look at concrete, it is made up of cement paste and it is with aggregate. And the aggregate, as you see here. Now, how do I get concrete to flow? One of the easiest way for me to do it is to increase water content. The minute I increase water content, my cement paste becomes less viscous and my aggregate starts aggregating. So what happens is, the minute I start adding water to concrete, my aggregates all start settling to the bottom. That's because the viscosity of the cement paste has decreased. So now how do I increase the flow while I retain my aggregate in suspension? And that now requires understanding the rheology of this complex suspension. And I'm working on some of these topics with some of my colleagues in chemical engineering. And even they are perplexed by the complex nature of this particular problem. Where how do you now hold this material in suspension? How do I hold the aggregate in suspension while I get concrete to flow? And the solution lies basically in use of admixtures. So we use admixtures which lower a rheological property called the yield stress. we reduce the yield stress so that the material can flow, while we increase the viscosity of this particular concrete mixture, so that we do not get the aggregate segregating out or separating out, so that I'm able to get this homogeneous flow from concrete. And of course, this rheology control comes with the use of several admixtures. I have to use water reducers, viscosity modifying admixtures. We use a lot of microfines in the concrete. We also use some retarders. So now what is happening is, to deliver on these performance requirements of concrete, I basically start selecting different admixtures and in order to deliver the performance. And I also start looking at engineering the material. I basically have to look at my concrete, start looking at how do I blend the cement and the aggregate together? What kind of material packing do I produce so that I can achieve these performance characteristics from concrete, so that it flows like water. It has a self-filling ability. Now, concrete made with this self-consolidating concrete, this is concrete which basically self-levels. It fills itself. It basically flows under gravity. I do not need to apply any vibration to get it to flow. The same precast girder, which was done with regular concrete, high slump concrete, is now done here with SCC. And you can see that concrete was able to fill all the small gaps between the reinforcement, the gap between the reinforcement and the formwork, and give us nice, shiny, smooth surfaces without any bug holes or any voids in the structure. Now, SCC, as it's called, self-consolidating concrete, basically flows like water, as it's shown here. And it's being used now to produce concrete, which is used in a form finish manner. That is, I place concrete, and whatever is the finish I get after I remove the shuttering or after I remove the formwork, it is put to use in the same way. So I can save on plastering. And I will just give you an example of form finish concrete, which we have implemented on our campus. So you also get an idea of SCC. So this video that I'm about to play shows the SCC that was implemented in on our campus. So this is the SCC mixture. So as you can see, this is concrete that is flowing by itself. It did not need any vibration. It is self-leveling. Basically, it's just like water. It levels itself. It flows. It fills all the gaps. So you can see that the concrete has basically gone between the gaps, between the reinforcement without any effort. And this gives you nice finished surfaces. And on IIT Hyderabad campus, in fact, we have produced buildings which with almost, which is nearly 6 lakh square feet of building space made with this self-consolidating concrete. And it's all form finished concrete where we have not used any plastering. So this is a technology that I'm happy that we are part of development and implementation on a large scale. Now, the other high performance requirements of concrete when it comes to formation, it's not just limited to high flowing concrete. The other extreme placement requirement can come in the form of very stiff concrete. If I can engineer concrete that is very stiff, then I can start making concrete pavements using an extruder machine like this. And this has become quite common now, where I take concrete which is also commonly known as zero slump concrete. This is concrete that is very, very stiff. It is simply put into this machine, and as the machine moves forward, it extrudes a layer of concrete pavement. And as you can see, as the machine is moving forward, this very stiff mix of concrete is retaining its shape. I don't need any formwork. I can basically start essentially extruding, starting laying a layer of concrete pavement, essentially just by moving the machine forward. But that requires me to engineer the early age performance of concrete, or the flow performance of concrete, or the fresh performance of concrete. The fresh performance of concrete required in this application is a very stiff mix. The concrete should keep its shape. It should basically, once the machine moves forward, once it's been extruded, it's been compacted, it's been finished, it should basically keep its shape so that I can keep extruding this concrete pavement as I move forward. This extrusion requirement is also used in precast industry. Hollow core slabs basically have a similar requirement. Hollow core slabs are also produced by an extrusion kind of a technology, as you see here. The machine extrudes concrete, and concrete is extruded with these holes that you see here. That's this is a typical hollow core slab. Now, the holes should not collapse on themselves. There's no formwork that's used. It's simply extruded with the holes, and the holes have to retain their shape. And the only way I can do it is by engineering the fresh performance so that I have a very stiff mix that keeps its shape. So that is again requires engineering the material using admixtures like water reducers, microfines, and retarders so that I can deliver that fresh performance that I'm looking for. Now, coming to fresh performance now, the last or the next step in the evolution of construction is the 3D printing. Now, what is required here? I have to engineer the fresh performance so that I can mimic the behavior of toothpaste. So toothpaste basically gives a very good example or an analogy for me to explain the requirement of 3D printing in concrete. Now, what does toothpaste have to do with the 3D printing? When we look at toothpaste, when I squeeze on the toothpaste on the tube, toothpaste flows out of the nozzle, and the minute I let go of the pressure, the whatever is extruded from the tube, it keeps its shape. So I'm able to basically extrude whatever is the shape of that nozzle from which the toothpaste is extruded. So this is exactly what we are looking for in 3D printing. I want concrete that when I pressurize it, it should flow, and it should come out of the nozzle, and it should keep the shape of the nozzle. And that is essentially what I have to achieve with concrete. Now, in toothpaste, people don't realize that to get the fresh behavior of toothpaste the way we want it, that is the toothpaste flows under pressure and it basically keeps the shape of the nozzle. The rheology of the material is engineered. Some world-class rheologists work on it, process engineers work on it to deliver that performance, or to get material that basically delivers that performance. We have to bring similar science into concrete, and that is what is being done in terms of engineering the fresh performance of concrete so that we can mimic this behavior of toothpaste into concrete. So basically we are entering into the domain of form-free construction then, where I can start extruding structures and delivering structures by building it layer upon layer. But that requires good rheology control in terms of pumpability, achieving non-segregated flow, shape retention, buildability. These are all aspects that we are now starting to talk about when we talk about 3D printing. And this, of course, requires good understanding of science, of rheology, material packing, use of admixtures to be delivering this kind of performance behavior. So rheology control admixtures that we are using in 3D printing applications include control of thixotropy, achieving low viscosity, high yield stress. These are all rheological properties that have to be achieved. And we use a mixture of admixture cocktail, basically. Several admixtures are used to tailor specific improvements in thixotropy or in viscosity or in yield stress. And basically what we are able now thinking of printing concrete structure is one layer upon it, one layer upon another layer. And basically we can assemble an entire structure made of concrete with this kind of technology. Just to give you, show you how 3D printing structures are being visualized. Here is a video of a structure that was printed in Singapore. This was a structure that was printed as demonstration when our Prime Minister visited Singapore, and an entire structure was basically assembled layer upon layer. So as you can see, the entire structure is being assembled layer upon layer. Now this of course requires tremendous engineering, a tremendous amount of engineering to achieve material that can deliver that fresh performance, to allow me to build one layer upon layer to assemble the entire structure. So, but there are of course challenges in 3D printing because we cannot have a pure concrete structure. So I need reinforcement. So the next challenge there is, and already groups in the world, around the world are starting to work on this, is how do I co-print steel and concrete together? Can I print a steel mesh along with concrete? And so that way we can do live construction of structures where basically now I feed the design to a robot and a robotic arm comes and basically prints out a concrete structure for me. That is the most efficient form of construction where I can speed up construction, use material most efficiently, and deliver structures in a very fast pace, or at a very fast pace. Now, of course, there are other ways that people are looking at, and the ways are is looking at embedding reinforcement into concrete. So why have external reinforcement in the form of bars? Can we use it in the form of discrete reinforcement in the form of fibers? So these are things that we are starting to look at, and to achieve form-free construction. So this is basically taking a drawing and printing a structure from a drawing. So that was as far as the fresh performance of concrete goes. Now, next thing I want to look at is what about performance in service? Now I have built my structure. I have to make sure that the structure delivers performance in the long run. It is a durable structure. Now here we are looking at enhancing the durability so that I can get a long lasting structure. And I'm motivating that by showing you this photograph of an aqueduct. This is an aqueduct in Nice in France. And this is an aqueduct that was built by the Romans 2000 years ago, and it is still in use today. So talk about performance and long-term durability. Such structures, if we can put to you construct today, would essentially ensure that I have a very sustainable development, because I'm putting structures which are very long lasting. So high performance concrete in service is basically becoming quite common, where we are now also putting performance requirements of concrete when it is in service. And I will just show you how we achieve this high level of performance when it's in service. So here now we have to talk about performance of mature concrete in terms of strength and durability. So again, we bring in a whole lot of admixtures that help us achieve this performance in terms of long-term durability. And there are again several admixtures that go from coloring admixtures so that we can color concrete, make it look beautiful, to all the way to corrosion inhibitors, shrinkage reducing admixtures. We are also using matrix densifiers, which basically densify the matrix and give us nice dense structures. And we're talking about add-ons like integral waterproofing and fibers, which basically make sure that if even concrete cracks, then basically the cracks heal themselves. So these are all things that we are now starting to look at as additions into concrete. And of course, when I'm talking about performance in the long term and durability, I have to talk about a lot of tests that are available. So now even the testing protocols are being enlarged. So gone are the days when we would only test concrete for strength. Now there are a lot of tests that are being developed for long-term performance of concrete, including permeability, chloride penetration, sulfate attack, and all of these are now becoming more common. Concrete is required to pass all these other tests as well. Now, just to show you that I can improve the performance of concrete for one specific application, which is chloride penetration, which becomes important in marine structures. So if I have concrete, control concrete here, where chloride has penetrated through concrete, I can basically reduce the penetration of concrete in this control concrete by adding some of these post-industrial waste materials like fly ash and GGBS. So basically the addition of these materials not only reduces the clinker factor, but also helps me in cutting down on the penetration of chloride through concrete. Now, the other problem that we have is cracking that is produced by shrinkage in concrete, because as I start making concretes which are self-flowing, self-leveling, then these concretes have contain a lot of fines. So I have to increase the fines content of concrete, and these concretes tend to shrink more. So basically you see that this is a concrete structure that is made with self-consolidating or self-compacting concrete. It basically cracked because it cracked from shrinkage, high shrinkage in the concrete. Now, I just want to show you that this is concrete that was engineered for performance. When I only looked at a specific aspect of performance in terms of penetration into concrete, penetration of chlorides into concrete and strength, the concrete nevertheless cracked, and it cracked because of shrinkage. So that means this is another performance attribute that was missed out. And you can see this is a bridge deck that was made from concrete, which is very dense, which it was very strong, but and it was also dense enough to prevent penetration of chloride ions through it, but it nevertheless cracked. Now the cracking, the reason for cracking was established to be shrinkage. And basically some analysis of this concrete bridge decks revealed that the concrete had high enough strength, it was uniform, and the cracks as they were formed in this bridge deck were basically formed all the way around the aggregate, which means that the cracks were formed at a very early age in concrete. So these cracks that result from shrinkage in concrete happen when the concrete is still within 1 week to 10 days after casting. So how can we cut down on these cracking? Adding fibers. A small dosage of fibers basically, and these polypropylene fibers that are commercially available now cuts down on these cracks that appear on the concrete surface. So I'm showing you that concrete without fibers has these surface cracks that develop, but if I add like 0.2% the volume of concrete in the small fibrillated fibers, I'm able to essentially mitigate this effect of cracking on the surface. So this is another admixture that is now, or these are fibers are also being added into concrete to control this aspect of cracking that happens because of shrinkage. Now, there are admixtures that are being developed to control shrinkage, and one of the admixtures that is being developed to control shrinkage of concrete is called shrinkage reducing admixture. And basically shrinkage is caused or produced because of surface tension effects of water inside concrete. And the best way to reduce a shrinkage is to reduce the surface tension of water. So the shrinkage reducing admixture essentially reduces the surface tension of water. And basically, I just want to show you here that if I add a small dosage, 1.5% the weight of cement in shrinkage reducing admixture, I'm able to reduce the shrinkage considerably, shrinkage in concrete, even with high fines present in it. So there are other kind of technology we are borrowing to mitigate the risk of cracking. And this includes the use of super absorbent polymers. Super absorbent polymers are basically the polymers that go into making diapers. They basically absorb a lot of water and they hold on to moisture. So now we are basically adding these super absorbent polymers into concrete so that they can release water to concrete when it is required. And concrete shrinks because it dries. So now, whenever I subject concrete to drying, if I can supply the water from the inside from a superabsorbent polymer, I can keep it from shrinking. So now superabsorbent polymers are being used by mixing them into concrete so that I can reduce the risk of shrinkage. And I just want to show you here that if I don't use superabsorbent polymers, this lowermost line shows the amount of shrinkage strain, the volumetric contraction, the shrinkage of concrete that's happening. If I add about 0.4% of superabsorbent polymer, I can basically reduce the strain down to zero. That means the shrinkage has essentially been cut down to zero. Now, the other things we're also using to cut down on the shrinkage of concrete, which are basically water reservoirs inside concrete in the form of expanded clay and shale or pumice, which are all porous rocks, which basically act like water release inside the concrete. So these are all things that we are looking in terms of mitigating cracking in concrete from different reasons. And typically, mostly concrete cracks in service because of load effects. Those are taken care of in the design, but also from material effects like shrinkage. So I have admixtures, I have other additives that I can add now to take care of cracking in concrete. But what if concrete does crack? Then now we are looking at autogenous self-healing and self-sealing of cracks. Self-healing is basically when I have a crack and the crack gets filled up with some material which prevents water ingress or which prevents water from getting into the cracks. And integral waterproofing essentially lies in this category where I'm able to seal the cracks. Now, but we are thinking one step forward where we are talking about self-healing. So this is basically mimicking what human body does. It's not just enough to seal the cracks, but then I should recover the original strength of concrete before the crack happened. So self-healing is now essentially talking about restoring the capacity of concrete after it has cracked. And this now is bringing in technology in the form of bacterial concrete, where we are mixing bacteria into concrete. And when the bacteria is exposed to atmosphere, it secretes calcium carbonate, which basically seals and heals the concrete. So this again is taking us into domain where we're interfacing with biology and microbiologists in order to produce a viable solution that is workable in concrete. Then we're talking about coloring admixtures. We're talking about concrete, which basically, rather than paint from outside, we use pigmentation to give it the color. And this is long-lasting color because this is concrete that has been produced with this color on the inside. Now, so we are now entering into the domain of nanotechnology. So how do I now produce self-healing, self-sealing, self-scrubbing concrete, self-cleaning concrete? We're talking about the use of nanotechnology. Nanotechnology for improvements in strength, self-sterilization. Self-sterilization has become very important, particularly in the COVID scenario, where can I produce surfaces which are self-sterilizing so that I don't risk some infection or these germs, microbes getting transmitted through the surface. Durability and internal self-repair. So use nanotechnology for this purpose. So cement with nano infusion is being thought of for improved performance. And basically we're looking at cement now so that we can produce this material and start competing with ceramics and high strength composites. It's not just limited to use in concrete, essentially elevating the status of Portland cement to a high-tech material. So that's what we are, the material scientists who are working in cement and concrete, that's what we are now currently working on. And to give you an example, cement which is infused with titanium nano titanium dioxide crystals has already become a reality. Now, titanium dioxide is a photocatalyst. If it is exposed to atmosphere or it is exposed to sunlight, it has the ability to scrub the or basically clean the environment of the harmful NOx gases. So what is done is that cement contains these nano titanium dioxide crystals, and when the cement surface is exposed to sunlight, it basically cleans the air which is in the immediate which is immediately in contact with the cement surface. So the cement surface becomes self-scrubbing, self-cleaning, and it also has now this sterilization effect. So this is now actively being looked at as something that, because it is self-cleaning, it does not need, it does not accumulate dust. It basically does not accumulate, it does not need painting. It looks fresh in the long term. So this is the other advancement in technology, using nano technology for producing commercially viable products. So, and the last thing I want to leave you with is this topic of active control of concrete. So while we're talking about performance of concrete structures and fresh flow, can I do something where I can engineer the flow that is set on demand? Can I throw open a switch and then let the concrete start hardening when I throw the set? So I have concrete which is fluid while I'm transporting it, while I'm pumping it. Once it's inside the formwork, I basically simply open a switch and it goes to into a set behavior. Now here we are working on the use of the magnetorheological fluids. So basically magnetorheological fluids behave differently under when the magnetic field is applied and when the magnetic field is removed. So we are trying to see if we can use nano infusion of this magnetorheological fluid, magnetorheological materials inside concrete, so that we apply a magnetic field and cause concrete or produce concrete to flow. When we remove it, it goes into a set behavior. It sets and becomes starts behaving like a set material. So that is the concept of set on demand. So a lot of active work is going on set on demand using electric impulses and magnetic impulses. So that is basically all the different performance related improvements that are being sought and are being developed for concrete, including fresh and the in-service behavior of concrete. What are the challenges that we face? Cost is the primary challenge. Now that we're bringing in complex chemicals into the picture, it does increase the cost. Black box. A lot of these chemicals that are being produced for achieving specific improvements in performance basically are being developed by chemists, and they are black boxes. They're very complex chemicals. And because it involves chemistry and we are civil engineers, we basically find it very difficult to understand this, but which also means that it opens an avenue. Now, as civil engineers, we have to invest the time and energy to learn the chemistry, to be able to engineer the chemistry to deliver the performance that we are looking for. Drug interaction. Well, this is something which is we notice when we take multiple drugs, they can interact with each other and produce harmful effects. When I'm using multiple admixtures, they can interact and produce undesirable effects. So we need to understand how these different admixtures interact with each other. Government is another issue. Government and policy. Government policy has not kept up to speed with the development of technology. So as a result, the use of this new technology is in the government sector is lagging. So, and that basically creates a problem because government is the largest stakeholder in infrastructure. It is the largest owner of infrastructure in this country. So unless the government steps forward and starts encouraging adoption of this technology in a fast manner, it's not going to be adopted. And the final thing is the cost to benefit ratio. So now that we're talking about performance, I cannot start looking at things just based on cost. We cannot start thinking of things as merely L1. We have to think of cost over the service life of the structure. So cost to benefit ratio. And when we do that, we may spend a little bit more money today when we use this new technology. But in the long run, if I'm able to get a structure that lasts 200 years as opposed to 20 years, then basically over 20 years, my investment more than pays off. In fact, I'm better off putting in that little bit of a little bit more money today. So that is the kind of thinking that has to be developed, where we start looking at our civil engineering projects from a cost to benefit perspective, rather than a cost today or an L1 kind of an evaluation. So with that, I'd like to conclude and say that concrete it's not 1:2:4 concrete anymore. We've come a long way. Concrete is now a respected composite material with tailored delivery of performance. I can now make concrete, engineer concrete to deliver the performance that is required of any high performance material. And concrete technology is serious business now. So with that, I'd like to conclude with this slide here. This is a slide, this slide basically shows a car, it's solar powered car, the chassis of the car is made of cement. 95% by weight of the material that went into making this chassis is cement. And this is a car that was actually produced with the cement-based material, which has a very high tensile strength. You see the solar panel on the back. It actually competed in this race, which basically traverses the continent of Australia under solar power. The car was entered as an entry from a cement company. It actually finished the race. So this is likely the vision of future for cement, where we're looking at cement and concrete as an engineered material. We can start producing cement components just like we do any other component made of steel or aluminum or ceramics. So with that, I'd like to thank you for your attention and take any questions that are there.
Thank you very much, sir. But no question answers for the endowment lecture, sir. So really explained very well about the concrete, sir. That's challenges of cement product and carbon footprint with production and energy requirement, and also alternative cement production and challenges in construction methodology, performance-based design, and performance measures in concrete, flow pumpability, and also high performance concrete and specification and performance required. Really, sir, it is almost you covered total subjects, sir. We have really enjoyed the talk, sir. With the few words, I'm requesting all of you, please give the big round of applause to our Subramaniam, sir.
Thank you. Thank you.
Now, I'm requesting that if Captain Janardhan sir is there, please talk 2 minutes only, sir. Already, sir has taken 1 hour, 10 minutes, 15 minutes, sir. You are really, without stop, 1 hour, 15 minutes you have taken time, sir. Generally, the endowment lecture will be only the half an hour, sir. Okay, anyway, everybody are with the interesting subject. That's why they all are enjoyed the talk, sir. Now, I'm requesting Captain Janardhan sir, please say few words within 2 minutes, sir.
Okay. Good evening, everybody.
Good evening.
We just now heard endowment lecture of Sri Gurram Koti Reddy garu. I think it is appropriate time to remember his greatness and his great deeds in the irrigation department. I am fortunate enough to work as Deputy Executive Engineer when he was SC Hyderabad Circle. He was the real taskmaster. He was responsible for supplying drinking water to Warangal city in record time. Before he took over, the importance in work was given to economy in execution of work, irrespective of time consumed. The result was that contractors used to quote less rates and get the work, and then try to get the estimates boosted up by illegal ways. And when that was not possible, they used to abandon the work. So getting the balance work through other agencies at a higher rates, penalizing the first contractor was never an easy job. Finally, it resulted in abnormal delay in completion. So Mr. Koti Reddy changed this practice. He first got the estimates prepared at workable rates and told the tenderers to be careful while quoting. He told them clearly that all the contractors will be engaged on different reaches, so without any unnecessary competition between them. Thus, having good rates, they could deliver the work in time. Thereby, he could supply the drinking water from Lower Mane division to Warangal city, nearly 90 kilometers. But one thing, in record time he could give it, because the time was fixed by, in 83 by Ugadi, the work should be completed and water should be given, and he has given it in time. He never, but one thing is sure, but he never overlooked the quality of work. He was very strict for qualities. Finally, of course, Unfortunately, he was retired at the age of 55 years only because of change of service rules at that time, which were later again changed. And I remember on his retirement day, there was a meeting like this, and what I told I still remember, and the same thing I will repeat. I said, Yaddad Acharati Shrestha Tatta Devyotaro Janaha Sa Yat Pramanam Kurute Lokastad Anvartate. He, whatever the great men, whatever they do, that will be followed by others. And the standards set by them will be followed by others. Mr. Koti Reddy has set standards very well, and we will try to emulate whatever the thing he has followed. Thank you.
Thank you very much, sir. Now I am requesting Engineer T. Anjaya, please propose the vote of thanks. Sir, Koti Reddy sir, son is there, sir. Satyanarayana Reddy, please, if you want, talk 1 minute, 2 minutes. Satyanarayana Reddy. From his family member, Satyanarayana Reddy. Satyanarayana Reddy. Okay, now we propose the vote of thanks, Sanjay sir.
Respected chief guest, dignitaries on the webinar, distinguished guests, fellow fraternity, media friends, and family members of Koti Reddy Garu, ladies and gentlemen, it gives me immense pleasure to perform the pleasant duty of proposing vote of thanks. On behalf of Telangana State Centre of IEI, I convey our sincere and profound thanks to Professor V L SUBRAMANIAM Garu, Professor, Department of Civil Engineering, Indian Institute of Technology, Hyderabad, for making it convenient to this August presence and deliver the Engineer Gurram Koti Reddy second endowment lecture in a very lucid way on a very important topic. I convey our thanks to the guests, past chairmen of Institute of Engineers, past presidents, and joint honorary secretaries, and our friend Sri V Jambul Reddy Garu, and our chairman Dr. G. Rameshwara Garu, budding engineers who made it convenient to be with us, to pay respects to Engineer Gurram Koti Reddy. I thank the managements of media for their continued support to all our endeavors and activities. I convey once again thanks to everybody.
Close with the Janagana Mana.